Hello everyone, I'm Zhiguo Jiang from Huazhong University of Science and Technology. It's my pleasure to introduce our work to you. The title of our work is OXO, a scalable and efficient graph stream summarization. Graph stream is a special big data model which refers to an infinite edge stream, modeling the interactions between entities, and it is widely adopted in big data analysis applications. Each tuple in the graph stream represents a direct edge which is generated at time ti. These tuples form a fast updating graph. Graph stream is widely used in various applications because of its general format and powerful expression ability. For health applications, over 1 billion scans are generated every day during COVID-19, which brings great challenges to the query of close contacts. For Alice e-commerce platform, the peak number of transactions during the Double 11 day is as high as 583,000 per second, making click farming detection pretty difficult. These applications replicate the features of vast volume, high velocity, and continuous updates with unknown boundaries of graph streams. In order to achieve efficient storage and query of fast updating and large-scale graph streams, the summarization structures compress the scale of the graph by aggregating the nodes in the original graph into supernodes in the summarized graph. The Hashi-based summarization structures use a Hashi function to establish the mapping relationship and then use the adjacency matrix, we call it compressive matrix, to store the summarized graph, such as TCM. The minimal description length-based structures use minimal description length to measure the memory cost of the summarized graph, and use heuristic strategies to update the mapping relationship whenever an edge is inserted to achieve smaller storage costs. However, the heuristic updating strategies have much higher computational overhead and cannot guarantee the compression rate compared with Hashi-based structures. Hashi-based summarization structure has been extensively studied due to their computational and storage efficiency. In order to solve the extremely high error caused by the Hashi collision of TCM, GSS generates a half-bit binary fingerprint for each node, and the edge will store the fingerprint pair of each endpoint to distinguish the edges mapped to the same storage bucket. At the same time, multiple candidate buckets are allocated for each edge to improve the utilization of the compressive matrix. In order to efficiently process the graph streams with highly skewed node degrees, S-Cube adds an efficient high-degree node detector on the basis of GSS, and dynamically allocates more candidate buckets for high-degree nodes to improve computing efficiency. In order to support efficient time-range queries of graph streams, Hora maintains multiple compressive matrices with different granularities, so that a time-range query can be decomposed into logarithmic scale subrange queries. However, all the Hashi-based summarization structures use a set predefined compressive matrix as the storage structure, which is not scalable when facing volume dynamically increasing graph streams with unpredictable boundaries. Moreover, simple scaling schemas such as chain-style scaling lead to linearly increasing computation and storage overhead, and it is also a great challenge to ensure the memory utilization whenever the structure scaling. To solve this problem, we designed a scalable and efficient graph stream summarization structures and supports efficient storage and query of dynamic graph streams. In order to verify the poor query and storage efficiency of the existing works when facing dynamically increasing large-scale graph streams, we conduct experiments to evaluate the performance of GSS, the state-of-the-art graph stream summarization structure, following the linearly expanding schema. In the experiment, we used the hyperlink network in the UK domain for the United Kingdom of 2007, which contains billions of edges. The figure on the left shows the memory cost of GSS chain increases linearly with the volume of a graph stream. The figure on the right plots latency for different queries. We can see that GSS chain is nearly 10 seconds to process a node inflow query, which is unacceptable in real applications. To avoid the linearly increasing space and time costs in a chain-style scaling structure, we propose a prefix embedding structure, PET. PET extends the new compressive matrices level by level in a tree style, and in the new level, edges with the same fingerprint prefixes are stored in the same compressed matrix. On the one hand, PET omits the common binary prefix of the fingerprints by embedding the prefix information inside the tree structure, and solves a significant amount of space costs. On the other hand, a query index is constructed based on the fingerprint prefix, which reduces the computational overhead to the logarithmic level. PET achieves high memory and computation efficiency. However, the exponentially scaling of the basic PET can have unsatisfied memory utilization whenever initializing a new level due to the large fraction of unused buckets on the new level. To improve the memory efficiency of PET, we first design a lazy expanding structure for PET. The lazy expanding structure organizes the matrices of PET into a binary tree structure and alternately embeds the fingerprint prefixes of the source and destination node, which make a good trade-off between memory utilization and time efficiency. The figure shows lazy PET has a more stable memory utilization. Based on lazy PET, we propose proportionally incremental strategy to further improve the memory utilization. Especially, we elaborate an auxiliary structure called deputy tree to convert the exponentially expanding of a new level into a proportionally incremental sequence. We call the binary tree structure of the lazy expanding PET the main tree. Here, we show a simple example of how the main tree extends to level 2. The whole process contains 4 phases. In phase 1, we generate only one matrix 0 for the deputy tree. In phase 2, when matrix 0 is full, we generate 2 matrices on the level 1 and move the edge stored in matrix 0 to the matrix on level 1 according to the fingerprint prefixes. Then we free the memory of matrix 0 and only keep the points. Such edge moving and memory-free operations continues in phase 3. In phase 4, we notice the deputy tree has generated the last level of the main tree. We just cut the last level of the deputy tree off and relate it to the main tree. The edge moving operation is efficient because it is performed with contiguous memory space and without edge relocation. We extending to a higher level. The proportionally incremental style of the deputy tree achieves much better memory efficiency when exponentially extending style of the main tree. Based on the PET structure and the proportionally incremental strategy, we propose OXO. OXO provides 2 basic topology queries for graph schemes. The first is the insert and edge query. They have similar operations and the same time complexity. Edge query returns the accumulated weight of an edge. When inserting or querying an edge, for PET structure, we need to check only one matrix per level from the root to the leaf according to the edge's fingerprint prefix. It's clear to see the time complexity of such an operation is a logarithmic scale. Given a node V, node inflow query returns the aggregated weight of all the edges pointing to V, and the node outflow query is similar. For the PET, we check matrices from the root to the leaf level. We take a node outflow query for example. If the last level embeds the fingerprint prefix of the destination node, we should check both children matrices of the current matrix, like we should check the two matrices on level 1. Otherwise, we only need to check one children matrix on the next level, like on the level 2. With each node query, OXO can support more graph topology related queries like a reachability query. We implement OXO and make the source code publicly available in GitHub. In the experiments, we use 5 real-world large-scale graph stream datasets containing billions of edges. When compare OXO with GSS, S-Cube, Horo, and like Moso and SGS. The matrix mainly contains latency average relative level error, which measures the accuracy of aggregation queries like the edge query and the node query. Time accumulated allocated memory TAM measures the overall memory overhead for a graph string summarization structure that scales with time, which defined as integral of the allocated memory over time. True negative recall measures the precision of the reachability query. We first examined the latency of insert operation, and both OXO and OXO Pro reduce the latency of GSS chain and S-Cube chain by 1 to 2 orders of magnitude. Then we test the basic queries. Both OXO and OXO Pro reduce the edge query latency by 1 to 2 orders of magnitude compared with GSS chain and S-Cube chain. And the examination of node inflow query shows our OXO design reduced the load query latency by about 1 order of magnitude. We compare the memory costs of different structures. The results show our OXO design reduced the memory cost of S-Cube chain and GSS chain by 50% and 15% respectively. The normalized TAM shows that the proportionally incremental strategy reduced the overall memory overhead of basic OXO by 34% on average and improves the average memory utilization over 20%. Then we test the query error. The results show that we can guarantee accuracy by adjusting the length of the fingerprint and achieve a pretty low level of average relative error. Moreover, we compare OXO with Horo and the state-of-the-art MDL-based work like Moso and SGS. We can see OXO has the lowest insert latency and reduce the memory cost of different structures by more than 1 orders of magnitude. Finally, we take the reachability query as example to examine the efficiency of our design on complex graph queries. We can see the true negative recall is pretty high and also reduces the query latency of other structure by about 1 order of magnitude. In conclusion, we propose OXO, a scalable and efficient graph stream summarization structure. Besides, we designed a prefix embedded tree structure for efficient summarization structure scaling, reducing the query latency to logarithmic scale and saving logarithmic scale of space costs. Moreover, we propose proportionally incremental strategy which scales a new PET level in an incremental way to guarantee high memory utilization with structure scaling. Finally, experiment results demonstrate the superiority of OXO compared with the state-of-the-art designs when facing large-scale graph streams. That's all content of my presentation. Thank you for your listening, and any question will be appreciated.